Hi, and welcome to our introduction to stochastic gradient boosting for classification. So before you watch this video, I recommend that you first watch the video Introduction to Cart Decision Trees for Classification, because as we'll see, CART forms the foundation for stochastic gradient boosting. So the main idea of stochastic gradient boosting is to iteratively fit CART trees to what we call generalized residuals. Now, the creator of this technique is Jerome Friedman, who's pictured here. Now, Dr. Friedman also co-created CART decision trees, he created Mars regression splines, and he co-created rule learner rule ensembles, which are some of the other techniques in our software. Now, the SPM modeling engine that implements the stochastic gradient boosting algorithm is called TreeNet. And in fact, the TreeNet code was actually originally written by Dr. Friedman himself. So stochastic gradient boosting is the formal name of this technique, but often it's just called gradient boosting, gradient boosted trees, or sometimes just simply boosting. Now, as it turns out, there are actually different types of boosting algorithms, so what I'm going to use, I'm just going to call it either gradient boosting or gradient boosted trees. Now, stochastic gradient boosting, as we'll see in this video, is very flexible, and it can handle things like regression problems, classification problems, survival analysis problems, and even more. Now, the reason we're going to use gradient boosting is because it is one of the most powerful machine learning algorithms in existence, and it's also fast, even for large data sets. And because CART serves as the foundation for gradient boosting, you can also build models with dirty data. Now, this video concerns gradient boosting for classification, but as it turns out, in my opinion, the best way to understand gradient boosting for classification problems is to first understand gradient boosting for regression problems using the least squares loss function. Now, the reason is because the formulas used in classification are not intuitive. They only really make sense unless you derive them mathematically, and since we're certainly not going to do that in this video, so what I'm going to do is I'm going to first explain gradient boosting for the least squares loss function, which is actually used in regression problems, and then we will extend this to the classification case. And as we'll see, the formulas are just going to change. Now, perhaps in another video, we'll explain the formulas and how you actually derive them, but that'll be something for a different day. Now, before we move on, just one thing to note here is don't use least squares for classification problems. Only use the least squares loss for regression. We're just going to use it here again just for the purpose of explaining the algorithm. Now, since we're going to explain gradient boosting for the regression case, I'll give you a quick recap or introduction to CART for regression. Now, we do have a video called Introduction for CART Decision Trees for Regression, and so you're certainly welcome to watch that, but if you didn't watch that video, that's okay. So here I'll just give you a brief crash course. So the idea here is to divide the data to better predict now the quantitative target, and the predicted values here are just going to be the target average. And what I mean by that is once you divide your data, you're going to be left with these y values. And so here what you do is you just take the average of these two y values, and then you're going to get this predicted value. And remember, we have n equals 2. We have 2 observations here. Also here we have 14 values, so n equals 14. If you take the average of these 14 y values, then you're going to get this predicted value, which is here. Okay, now for classification, again, here the idea is to divide the data to better predict the categorical target. The predicted value is going to be a probability, and the splitting criteria is now going to be based on node purity, and we talked about this in the last video. So this is just kind of a side-by-side here. Okay, so for the least squares loss function in gradient boosting, what we're doing is we're actually fitting CART trees to the residuals from the previous step. And here the least squares loss function is just the squared error here. Y is the actual value, y hat is the predicted value. And so the way that the gradient boosting algorithm for least squares works is that we supply an initial value, which is just the overall average of the target variable. And then we sample some records randomly. And then for those records that we sample randomly, we fit a CART tree to the residuals from the previous step. And then we use that to update the model, and we shrink the update by a small number. And then we just repeat these steps 2 through 4 m times. Now we're going to go into a more in-depth example for the algorithm. So, as I mentioned, for the least squares loss, the initial prediction is just going to be f0, which is just going to be the average of the target variable for the records in the learned sample. And so here, f0 is just going to be y bar. Now what we do is we draw a random sample from the records in the learned data, just here. And then we compute the generalized residual, which is just yi minus y bar for the records that we drew in our sample here. And so you're going to have something like this. So you have this variable y tilde. And now what we're going to do is we're going to use this y tilde that we just calculated as the target variable. And so what we're going to do is we're going to fit a small unpruned card tree with j terminal nodes using the records in S to this generalized residual. So you'll have something like this. And then what you're going to do is you're going to use this tree that you just constructed to update the model. So for the least squares loss, the updates are just going to be the target variable average for each terminal node. And we'll explain what this means next. But for now, just to note the updates for iteration 1 by cart 1. And so for step 4, what we're going to do is we're going to shrink these updates by multiplying by what we call the learning rate. Now the learning rate is really just a small number, and we'll talk about a little more about that later, but really just for now, just think of it as a small number like 0.01. So we're going to shrink our updates by that small number. We're going to add it to our current model, which is just this f0 here, and this will be our updated model. Now, of course, we know the formula for f0, so we can just plug in. And so this is our updated model after iteration 1. Now for iteration 2, we do the same thing. But now our current model is this f1, which is just our y bar plus that alpha times the cart 1. So draw your random sample. And then for the records in the random sample, compute the generalized residual. Now you may be asking, well, how exactly do you compute a generalized residual? Like, for instance, yi is a number, y bar is a number, but what is this alpha times cart 1? What does that actually give you? Well, just to remember here, this is our current model after the first iteration. And remember, cart 1 is just the tree fit to the generalized residual during the first iteration. And the generalized residual during the first iteration was just yi minus the y bar. So our current generalized residual is given here. And remember that alpha is just that small number, like 0.01. So let's just for now suppose that cart 1 is this tree. And so also we'll give a value for y bar just to make things simple. Maybe call it 40 and maybe let alpha be 0.01. Then let's say that we have some randomly selected record. So what we're going to do, to compute the value for cart 1, we're just going to run this record down this tree and look at the terminal node average, which is the predicted value, as I described earlier. So take this record and then run it down this tree. So our first rule here is x2 less than or equal to 17.5? Well, here x2 is 12.5, so that's a yes. So we can come here. And then is x1 less than or equal to 355.8? Well, here x1 is equal to 400, so we're actually going to go to the right here, where x1 is greater than 355.8. And so our value for cart 1 is just this number, this negative 2.027. So our generalized residual we can now compute. And so y we have, which is just given here, this is 39. Y bar, we let y bar be 40. We also let alpha be 0.01, so we can plug in for y bar and for alpha. And now cart 1 we just computed to be negative 2.027. And so our generalized residual for this record is just given by this. Now what you do is you just repeat this process for all the records selected in step 1. So remember, step 1 is where we just draw a random sample from the records in the learned data. And so that's why we have this randomly selected record, and I gave you the following values. So that's where that record came from, just in step 1. Okay, so now we know how to compute the generalized residual. So what we're going to do is we're going to use that generalized residual as our target. And we'll fit a cart tree to that target for the records that we sampled in the first step. So we have our sample, fit your cart tree, And now we're going to use this tree to update the model. And for the least squares loss function, the updates are the target variable average for each terminal node, as we discussed previously in the previous slide. So we're going to denote these updates for iteration 2 by cart2. And then we'll do the same thing we did before. So we'll shrink them by alpha, which is our learning rate, and we'll add them to our current model, which is now F1. Our current model is here. So our updated model is now going to be called F2, and it's just going to be F1 plus the alpha times the cart2. Now, of course, we know the formula for F1, which is given here, so we'll plug in, and this is our updated model after iteration 2. Now for the third iteration, you can probably see the pattern, but let's just run through it again. We have our current model, F2. Draw a random sample now from the records in the learned data. Compute your generalized residual now for y minus F2. And then we're going to use this generalized residual as the target, and we're going to fit a small unpruned cart tree with those J terminal nodes using the records that we sampled here. So fit your tree. That's going to give you another update. We'll call it cart3 in yellow here. Multiply the predictions from step 3 by alpha and add them to our current model, which is just F2. And then that way you can get F3. Now, of course, we know the formula for F2, which is just here. So plug that in and you get this. Okay, so we'll skip to the last iteration. And so note that there are a total of m iterations for gradient boosting, and in practice the user is going to specify the m. So the current model is just going to be this up to m minus 1. And so take your random sample, compute your generalized residual now for y minus fm minus 1, and then use that value as your target and fit your cart tree again with those J terminal nodes. And then we're going to use that tree to update the model and multiply the predictions again by the alpha and add them to our current model, which is here, to get your updated model. Now, of course, we know the formula here for fm minus 1. It's just here, so just plug in, and then you get this. And so this is actually our final model here. So, just as a brief summary, this is the summary for the least squares loss. So you may be asking, well, how do you go from least squares to classification? So we're going to do that now. So first, this is for the binary classification loss. So the first thing naturally that's going to change is the loss function. So we're going to go from the least squares loss function here to the binary classification loss function, which is here. Now the initial value is no longer going to be the target variable average. It's now going to be the overall 1/2 log odds. And our current model thus will have to change. So we'll no longer have the y bar. We're going to have the 1/2 log odds. Now the generalized residual is no longer going to be just the typical definition of the residual. It's actually going to be this. And maybe in another video we'll talk about how to get this formula, but that'll be something for a different day. Now the updates are no longer the target variable average. Now they're going to be given by this. And so our final model will have to change as well. And so it'll just be, we'll have a different intercept here, and the trees themselves, of course, will be constructed in a different way. And so here, this is gradient boosting for the binary classification loss. Okay, so how do we predict new records in gradient boosting for classification? Well, this is our final model after m iterations. So note here that m iterations corresponds to m card trees, so that's something important to keep in mind. Now, depending on the software that you use, you're either going to see number of trees or number of iterations. For TreeNet software, we actually just use number of trees. So predicted values in a gradient boosted tree for classification come in two forms. So one is the 1/2 log odds, and the other is probabilities. Now to predict a new record, what you do is you run the record down each tree here, and each time computing a prediction that's on the 1/2 log odds scale. So really keep this in mind. Now the reason it's on the 1/2 log odds scale is because our starting value is the 1/2 log odds, and the rest of the trees are just adjustments to this value. So that's why it's on the 1/2 log odds scale. And so you're going to run the record down each tree. And so run down cart 1, you get a prediction, cart 2, and cart n-1, and cart m, and so on. Now multiply each value here, except for the initial value, which is just an orange. Remember, this is just our initial 1/2 log odds. And you're going to multiply this by the learning rate. Now, in the third step, just add the values from step 2, and just go ahead and let alpha be 0.01, just so you have a number here. And so this here, this is your prediction for the 1/2 log odds scale. So this is the first part here. Now the final prediction here is a probability. And we obtain a probability just by transforming the number from step 3, which is on that 1/2 log odds scale. And so the probability for like y equals 1, which is, now when I say y equals 1, I really just mean y equals the class of interest, is just given by this formula, which in this case is just 0.09, which is just 9%. So just to recap, the two forms, one is the 1/2 log odds, which is what you see here in step 3, and the second is probabilities, which you see in step 4. Okay, so we just saw the gradient boosting algorithm using the least squares loss and the binary classification loss, but gradient boosting is actually more general in nature and can handle a variety of loss functions. Now, of course, as we just saw for the binomial and least squares example, the choice of the loss function will change the formulas used for the initial values, generalized residuals, and the model updates. Now, when you're fitting gradient boosted trees, just remember that you are sequentially fitting m number of cart trees to generalized residuals instead of the original target, and that you're also shrinking the updates by alpha. And remember, alpha is just that small number that we gave the fancy name of learning rate. And so just kind of keep this picture in the back of your mind. Now, because the foundation of gradient boosting is cart, gradient boosted trees actually automatically handle the following. So things like variable selection, interaction modeling, local effect modeling, and the nonlinear relationship modeling, missing values, outliers, and the fact that they're not affected by monotonic transformations. All of these were just the cart advantages that we discussed in the previous video. Now, one thing I will note though is that missing values are handled differently in gradient boosting than they are in cart. And perhaps we'll go over that in a different video, but for now, just know that they're handled slightly differently. Now, there are some parameters to consider when you're building gradient boosting trees, including the number of trees, the learning rate, the subsampling fraction, and the tree depth. So remember that each iteration in a gradient boosted tree model corresponds to a single cart tree fit to the generalized residuals from the previous iteration. And so the number of trees, what you want to do is you want to set it high enough so that the model error converges. And sometimes you are going to see that after a certain number of trees, the test error is actually going to start to increase. So you'll start to see it decline, 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 and then it'll start to go up. And if that happens, then you just want to choose the number of trees corresponding to the minimum test error. Now, note that the optimal number of trees will actually depend on the values for the other parameters. And now when you want to set the number of trees in the software, go to the TreeNet tab here, and you can go to this number of trees to build setting here. So to give you an example of the choosing the number of trees, let's look at this error curve. So here, the maximum number of trees is 400, so we stop at 400 here, but the optimal in terms of the misclassification rate is 399, which is this purple line you see here. And you can also see it here in this table. Now, because the 399 is obviously very close to the 400, which is the maximum number of iterations, it's a good idea to refit this tree with the same settings, but just increase the number of trees. And so that's what I actually did here. So here I fit the same model, but now with 1,000 trees. And so we can see now that the optimal number of trees for the misclassification rate is actually 410. So you can see that here. And as far in terms of the other model metrics, they're all much lower than 410. So we can actually be sure of those. So this is just something to kind of keep in mind when you're fitting these gradient boosted trees, is you may just need to fit a model with lots of iterations, or even it stops well before the maximum number, it's okay, because the model you actually use will be the optimal one here when you actually use it to score new data and look at things like plots and things of that nature. Okay, so another parameter to consider is the learning rate. So the learning rate, which here is just denoted by alpha, which we can see here. Remember, this is just the amount of shrinkage applied to each model update in the jth iteration. So here, it's actually in step 4. Remember, the learning rate was just that small number. So sometimes you'll see that the learning rate is actually referred to as the shrinkage, because the learning rate, remember, is just that small number. It's between 0 and 1. And so the closer to 0, the more shrinkage you have of the model updates. Now, choosing the optimal learning rate is accomplished through cross-validation or via some type of testing sample. But in general, what you want to do is you want to keep the learning rate small, and values like 0.001, 0.01, or 0.1 often give good results. And one thing that you should be aware of is that smaller learning rates require more trees for the test error to converge. Now, as to why that is, let's discuss that now. So, now in gradient boosting, the learning rates are set to be smaller, as I mentioned before, and those smaller learning rates will require more trees for the model error to converge. And so the intuition here is that, imagine that you want to walk to the middle of a crater. Now if you take small strides, which means you have like a smaller learning rate, then you will need more steps. And so more steps would be like more trees in this case. And you'll need that to get to the bottom of the crater. Now what I mean by bottom of the crater is just the minimum model error. Now if you make a mistake along the way when you're walking to the middle of the crater, which means that like the model makes an error during one of the iterations, then the error is not as serious because your stride is smaller. And what that means is that it's easier for your model to recover in the next iteration because the mistake is minor. Now on the other hand, if you take larger strides, which corresponds to a larger learning rate, then you'll need less steps to get to the bottom of the crater. The problem though is that if you make a mistake, then the error now is more serious because your stride is larger. So you may have pushed too far in a certain direction and your model may have a very hard time of recovering from that. So that's why we want to keep the learning rate small. And so the main takeaway here is that with each iteration, gradient boosting just improves slightly. And the result of these hundreds or even thousands of small improvements is a very powerful model. Okay, the next parameter to consider tuning is the subsampling fraction. So remember that in the first step here of our algorithm, we draw a random sample from the records in the learned data. So the first question is well, why even do that in the first place? So taking a random sample at each iteration, what it does is it decreases the correlation between the trees at different iterations, and what this does is this in turn tends to reduce the overall prediction variance of the combined model. Now, how large should this random sample be? Well, it kind of depends on the data set. And so the default value is 50%. And note that when you have smaller percentages, this leads to faster model compute times. And the reason is because there's a smaller number of split points to evaluate. And so here's how you set the subsampling fraction in the software. And if you want to experiment with different values for the subsampling fraction, then you can do that here. So what this is going to do, this is called automate T in subsample. What this will do is you'll build multiple gradient boosted tree models, but each time you're going to change the subsampling fraction, and you can see how the model error is affected. Okay, so the last parameter that we'll discuss is the tree depth, and this is just the maximum number of terminal nodes per tree. So in gradient boosting, the user actually sets the maximum number of terminal nodes for each cart tree, and a cart tree with j terminal nodes can capture up to a j minus one-way interaction, but it's not guaranteed that a j minus one-way interaction will be modeled. So, for instance, if you set the maximum number of terminal nodes to be 7, then a gradient boosted tree can capture up to a 6-way interaction, but it's not guaranteed that a 6-way interaction will be captured. Now, in general, as the number of terminal nodes increases, the complexity of the interactions able to be modeled also increases. Now, to give you an example, let's look at this cart tree. So the picture of the tree on the left here is actually automatically produced with cart software. And to see that, just click, there's a splitter button in the bottom left of the results that allows you to see these types of diagrams. But now this tree diagram on the left shows a cart tree with 7 terminal nodes. 1, 2, 3, 4, 5, 6, and 7. Now, what the tree on the left does is it models the following. So it models a 2-way interaction between capital gain and relationship. And so to see that, that's just here and here. So this is one 2-way interaction. It also models a 4-way interaction between relationship, occupation, capital gain, and the education number, which is here. And it also models a 5-way interaction here between relationship, occupation, capital gain, the education number, and age. Now, so what this means is that a 7-terminal node tree here captured a 5-way interaction as opposed to the 6-way interaction, which is the largest interaction where they can be captured by a 7-terminal node tree. Now also, if you'll note here, I didn't have enough space to put all the lines, but we also have a 2-way interaction between relationship and occupation because we have this node here, and that's what that models, just that interaction. We also have a 3-way interaction here between relationship, occupation, and capital gain because you would end up in this terminal node. But the moral of the story here is that even though we have 7 terminal nodes, we only are modeling a 5-way interaction as opposed to the 6-way, which is the largest that it can actually capture. So how do we actually optimize that parameter? So an efficient way to select the optimal number of terminal nodes for each tree is just to use automate nodes. So what automate nodes does is it builds multiple gradient boosted trees, but it changes the maximum number of terminal nodes each time, so that you can easily determine the optimal value for the maximum number of terminal nodes. Okay, so now we're going to move into the last section of our video, and it concerns interpreting a gradient boosted tree. So since a gradient boosted tree is fundamentally a sequence of hundreds or even thousands of cart trees, there is not a tree diagram like there is with one cart model. Now, there are a variety of options for interpreting gradient boosted trees, including variable importance measures, partial dependency plots, interaction statistics, and rules. And today we're just going to focus on these two, the variable importance measures and the partial dependency plots. Okay, so the variable importance measures in gradient boosting are calculated by the following. So each time a variable is used to split the data, the split improvement is recorded. Now, a split improvement, which we actually calculate that for you in a separate video, this is just a measure of how well a certain split separates the target classes. Now, the variable importance measure itself is computed by summing the improvement scores every time a variable is used in any of the trees. So here what we can see is the variable importance list for a model that was built to predict whether or not someone is going to make over $50,000 a year. And so you can see that you have the raw importance scores here where we uncheck the relative importance box, and we also have the relative importance scores. Now, relative importance scores take a value between 0 and 100. And so the way they're computed is the following. So you just divide each of the raw importance scores by the largest score and then multiply by 100. So for instance, here we have the largest score, which is just 1. So take 1 divided by the largest, well, the largest is just still 1, multiply by 100 and you get 100. And that's where this number comes from. Now, if you take, for this variable, we have 0.34. It's actually 0.3406. There's some rounding here that you don't see. But divided by the largest score here, multiply by 100, and then you get 34.06. And so that's where this number comes from. Now the reason we use the relative importance is because of the interpretive value. So here we can say that relationship, which has a score of 100, is almost 3 times as important as the variable edu num, which is here. Now this relative comparison, all of these are relative to the most important variable. Okay, so the final topic concerns partial dependency plots. So partial dependency plots show how a variable, or set of variables, affects the average response of the model after accounting for the other variables in the model. Now partial dependency plots can be created for both categorical and numeric variables. And in the case of binary classification, the y-axis of the partial dependency plots is the average 1/2 log odds. Okay, so I want to first explain to you how they're constructed, and then we'll go into how to interpret them. So let's assume that we have built a gradient boosted tree. We'll call it Tn of x, Tn for treenet. So what we'll do is we'll sample a single record R. And again, this is the same data. This is the data set that's used to predict whether or not someone makes over $50,000 a year. So it's a binary target. So 1 for if you make over $50,000, 0 for if you make less than or equal to $50,000. Okay, so we sampled our single record, and we're going to hold every value in the record constant except for the value for the variable under consideration. So maybe if we want to construct a partial dependency for the variable age, then we'll leave everything constant and just change age. So the first thing is just plug the original record into the treenet model, which will give you a predicted value on the 1/2 log odds scale. And then now what you do is you plug in the record again, except for this time just change the value for age. So maybe make it 20, and then plug it in, you get this value. Maybe 25, and you get this value. 28, maybe you get this value. 41, and you get this value, and so on. So keep doing that. So keep changing age, as you can see here, and keep adding these predicted values. Okay. And then connect all of this into one curve. And then what you do is you repeat this process multiple times, which is going to result in multiple curves. So maybe you get a curve like this, and then you keep going, and maybe you end up with one like this. And so the final step is just to take the average of all curves generated to yield the final partial dependency plot. So average all of these, and you're going to get a curve like this. And so remember here that the y-axis is the average 1/2 log odds. So you can't have negative values here for the y-axis because the log odds, of course, can be negative. So to interpret the partial dependency plot, the main takeaway here is that between the age of 25 and 48, so around 25 here and 48 is about here, the likelihood of making more than $50,000 increases the most. And so more specifically, if you want to be really specific about this, you can say that on average, the 1/2 log odds of making more than $50,000 increases by around 0.75. Now the 75 you get from increasing from negative 0.5 to 0.25. So one thing to keep in mind is that you only use the partial dependency plot for examining the change in response. So you can look at things like, oh, well, what happens if I go from 20 to 60? And then you can compute the difference on the y-axis. But don't just plug in a value and then look to find the 1/2 log odds. That's not what this is saying. Because the actual value for the y-axis is actually going to depend on the values for the other variables. So this is really just a marginal plot. It's just showing you the increases for one variable while taking into account all of the other variables. So only use it for the change in y. So you can also generate bivariate partial dependency plots, and the way this is constructed is very similar to the univariate. So here you sample the record. You're going to hold all the values in the record constant except for the 2 variables now under consideration. And of course you can plug this record into the treenet model, and this will give you a predicted value. And then of course now you're just going to change both the values for the 2 variables under consideration, and this is going to yield a 3D surface. And then you're going to repeat this multiple times, and you'll take the average to yield the final partial dependency plot. Okay, so here we have our 3D partial dependency plot, and so the z-axis here, which is just this output that you see here, in this example, remember, this is still the average 1/2 log odds of making more than $50,000. And so what this plot tells you is that high values of this education number here and being over 35 years old result in, at least on average, a higher 1/2 log odds of making more than $50,000. So now one thing to remember is that as the 1/2 log odds of making $50,000 increases, the probability of making $50,000 increases. So that's just something to kind of keep in mind, if you're not familiar with the 1/2 log odds. Okay, so another way to view the partial dependency plots for two variables is to just view them as a heat map. And so I actually like to use this because I usually find this just a little easier to read. It's really easy to see like the value for the education number here. It's actually here like 13. And you can also look at the values for age that it falls under as well. So like the 35 here, you get from just looking at that directly. So it's a lot easier to see. Now this partial dependency plot still tells the same story. So high values of the EDU num variable and being over 35 years old result in, at least on average, a higher 1/2 log odds of making more than $50,000. Okay, so that concludes our basic introduction to stochastic gradient boosting for classification. And if you have any questions, then please feel free to contact us anytime at support@salford-systems.com. And I will see you in the next video where we will build a gradient boosted tree model using a publicly available data set.